Okay, here I am providing some examples of Brett's rule application. So the first thing we must remember that basicity is proportional to lone pair availability. So more lone pair available on certain atom, more is the basicity. If the lone pair is involved in any resonance or any kind of conjugation, of course the availability on that lone pair will be less and the basicity will be less. Now in the first example, in this compound, you can see here the lone pair can take part in resonance with the carbonyl oxygen, and it will look like this carbonyl will be formed. But we must check that whether this resonance is actually possible or not. So for that we have to do what, the n counting, and we all know if the n is greater than or equals to 8 for this bicyclic system, only then bridgehead position or bridgehead carbon can have a double bond or can be sp2 hybridized. Now here 1 2 3 4 5 6 n equals to 6, so clearly this resonance is not possible. And if this resonance is not possible, that means this lone pair is not in resonance with this carbonyl oxygen. That means this lone pair will be available for further donation, that is this nitrogen atom will be basic. So in exam, if such question comes, so don't just answer blindly like yes, it will take part in resonance and this nitrogen atom will not be basic, it will be basic. Now the next example, if such compound is provided in any exam and if there is any base, B represents base. So there will be two possibility. Since we all know base abstracts the acidic hydrogen, and in this compound, since the carbonyl group is present here, so the alpha position, these two are the alpha position with respect to this carbonyl. These two will be more acidic carbon and this hydrogen will be more acidic because of this electron withdrawing tendency. Now there is two possibility A and B. We'll first draw the carbanion. So if this base abstracts this hydrogen, this will be the carbanion, and this carbanion will be resonance stabilized. Why? Because here equals to n equals to 9. Now for better visual representation, I have actually drew this similar structure in this manner so that you can get a way better pictorial representation. So here you can count that n equals to 1 2 3 4 5 6 7 8 9. So this bridgehead carbon can have sp2 hybridization. And here also there is no such issue. This is not a bridgehead carbon, so of course it can attain planarity. So these two will be formed. Don't just answer like only this will be formed, this will not be formed, this will be formed. You have to just count the n. In the next examples, I have just drawn some carbocation, and we have to see whether this carbocation formation is feasible or not. In the first example, here there is no bridge, right? If there is no bridge, of course these three bond can be in the same plane. There will be no issue unless until there is some bridge. There just bridges pulling up two cycles, two rings, and there is some strain. So of course this carbocation formation is feasible. In the next example, here is the carbocation is in bridgehead position. First you have to check whether the carbocation is in bridgehead position or not. Yes, it is in bridgehead position. Now count the n, which is clearly 10. Of course, this is possible. In the example, this carbocation is in bridgehead position and here n equals to 11. You just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's possible. Here, if you check, the carbocation is not in bridgehead position. It is on the top of the bridge. Top of the bridge is not bridgehead carbon. Bridgehead carbon is what? The carbon shared by two rings. So here of course the carbocation formation is not of any issue. So the carbocation will be formed. And here also the another example, there is no bridge. So of course carbocation formation is possible. Next I have chosen example of stability of alkene. We all know that the alkene stability is directly proportional to the number of alpha hydrogen, or more number of hyperconjugation, more is the stability. Now these are the two alkenes. Now if you see here the alkene, so the alpha position, in the alpha position there are 2 alpha hydrogens, and here 4 alpha hydrogen. Now we all know that more alpha hydrogen, more will be the stability. So expected is 2 is the stability of 2 is greater than 1, but in actual 1 is greater than 2. Why? Again, this is the Bredt carbon. You just check 1, 2, 3, 4, 5, 6, n equals to 6. So clearly this double bond formation here is not possible. It is highly strained. It is not attaining the expected 120 structure that is very much needed. So the actual is 1 greater than 2. So these are the some examples I just tried to cover, and then in the next lesson I'll give further examples. There are many more examples actually. And let me know if you want to have a detailed discussion on any other topic. I'll try to provide. Thank you. Bye bye.